I can't see the. Oh wait. So
Mingxi,
yeah.
are you ready now?
Okay, I'm ready.
Fantastic. We are so
Okay.
excited, Mingxi, to just listen to you about the radioactive decay modeling and its application in the cancer therapy, which that's all which is very important now then. Yeah, please go on, and thanks a lot for preparation for this presentation. Thank you.
Okay, so morning guys. Today the content I'm going to talk about is radioactive decay modeling, which is another kind of mathematical model in math. At the beginning, I'd like to talk about its definition. So radioactive decay is also known as nuclear decay, radioactive disintegration, or nuclear disintegration, in the process by which an unstable atomic nucleus loses energy by radiation. Also, a material containing unstable nuclei is considered radioactive. There are three the most common types of decay, which are alpha decay, beta decay, and gamma decay, all of which involve emitting one or more particles or photons. And there are several
Mingxi, sorry to interrupt
yes.
you. Are you going to talk about in your coming slides that what makes the atomic nucleus stable or unstable? Which it means that why the atom, they call that isotope. Isotope.
Oh
Do you
yeah,
have,
I have.
you're going to talk about that, huh?
Yeah.
Okay, yeah, please go on.
And there are several areas we may use the knowledge of radioactive decay in our real life. To study the living organisms, to diagnose and treat a disease. And I will mainly talk about this point of how it were used to treat cancers, and to sterilize medical instruments and food, to produce energy for heat and electric power, to monitor various steps in all types of industrial processes. And also the tracers. The tracers are a common application of radioisotopes. A tracer is a radioactive element whose pathway through which a chemical reaction can be followed. Tracers are commonly used in the medical reaction can be a medical field and in the study of plants and animals. Radioactive, for example, radioactive iodine 131 can be used to study the function of the thyroid gland, assisting in detecting disease. So basically, radioactive decay are mainly used for produce energy and treat disease.
Mingxi, sorry to
Yeah.
interrupt you. That slide was super interesting. Honestly, it has years of doing research on any words which you have written. So much content. I have two questions. The first question is that you said iodine, it's used in the treatment of what kind of disease?
To treat the thyroid gland, thyroid. I don't know how to pronounce it.
Thyroid?
Yeah. thyroid.
Okay. Okay, sure. Thanks. And just please, when you're done with your presentation, just let me, text to me that word.
And then you have another question, right?
And also the other question,
Oh,
thanks for reminding me, the tracers which you talked about at the end. Okay,
yeah.
remind me at the end of your presentation, I have something very interesting for you, man. That's very
Oh,
interesting, tracers.
okay.
Thanks.
And then the transmutation process. A radioisotope has unstable nuclei that does not have enough binding energy to hold the nucleus together. So radioisotopes would like to be stable isotopes, so they are constantly changing to try and stabilize. In the process, they will release energy and matter from their nucleus and often transform into a new element. This process called transmutation. Uh, by the way, it is the change of one element uh, into another as a result of changes within the nucleus. The radioactive decay and the transmutation process will continue until a new element is formed that has a stable nucleus and is not radioactive.
Very nice.
And then this is an example of the graph of the radioactive decay. The N0 represents the initial amount of the nuclei, and the whole curve is constantly decreasing all the time. The number of the nuclei changes with respect to time, which is represented by t. And then we'll talk about the formulas. There are three different formulas, and each of them represent different things. Uh, so n equal to n times e minus delta t, and a equal to a times e delta t, and m equal to m times e minus delta t. Where n is the total number of the particles in the sample, and a represents the number of decays per unit time of a radioactive sample, and m is the mass of remaining radioactive materials. And the first formula, which is this one, is also known as the radioactive law. It is a universal law that describes the statistical behavior of a large number of nucleus. And the radioactive law states that the probability per unit time that a nucleus will decay in a constant, independent of time. This constant is called the decay constant and is denoted by delta. And these are several radioactive decay equations with different variables. Uh, so these are three equivalent equations that give the number of nuclei remaining at time t, where t 1/2 is the half-life of the isotope. And the second involves a variable t, which is called the mean lifetime or the characteristic time. And the third one uses a variable delta, known as the decay. It represents the decay constant. And the variable t 1/2 and delta are all related by the following equation, which is this one. Regardless of which variable or version of the equation we use, the function is always a negative exponential, meaning it never reached zero. For each half-life that passes, the number of nuclei is halved, becoming smaller and smaller, but never stop vanishing. This is what happens mathematically.
And that's an interesting thing, Mingxi, you said that
Yeah.
that radioactive modeling which we have, which is, let's say, the initial amount of the material radioactive, then you have the exponential form that e to the power minus, let's say, lambda t, then you can prove that. But just one question I have, because I just want to also, the fact which you say, it's totally correct. And I have also these questions for everyone else in the class, because it's very relevant to the asymptotic behavior of a function that we talked in the class. We talked about either the endpoints behavior or asymptotic behavior. We said that in that case, we have to find the limit of a single or multivariable functions when the t goes to 0. Then that's the thing that we talked about that. And now, the thing which we want to talk is that when we talk about the asymptotic behavior, when we talk about the asymptotic behavior, then the expectation which we have is that we take the limit. For example, we have the exponential decay. We have n naught e to the power minus lambda t. But remember that the fact that you say that, hold on a second, guys. Then you say that when sorry, I had to just interrupt. Sorry about that. Then we said that when we talk the n, for example, t goes to infinity. For example, when it goes to the plus infinity, then essentially you expect that the endpoint behavior n naught e to the power minus lambda t, t goes to infinity, then you expect that e vanishes, goes to 0, and you end up somewhere close to 0. Anyone sees that? People, students,
Yes.
do you see that? And that's the definition of the endpoint behavior. We said that t goes to infinity, it means that the time goes all the way, increases, but on the other hand, the approach, the curve of the function approaches to 0, epsilon distance from the 0, but it never gets to 0. It doesn't cross the x-axis. And that's a very crucial thing that we had to feel it when we talk about the asymptotic behavior of the functions. Correct?
Yes.
Awesome. Thanks a lot, Nijay, for bringing this up, because it was a thing that we had to, it was a cornerstone of our class when we talked about the endpoint behavior. And also when you go to the calculus class next year, that's when you talk about the asymptotic behavior. It's very important we understand that the mass of the radioactive material, because of the limit when t goes to 0, when t goes to infinity, doesn't become equal to 0. It goes close to 0, but never touches the x-axis. Yes?
Yes.
Fantastic point. Fantastic point. Thank you, Mingxi. Please continue.
Uh, and then, which page? Oh, 8. And then I will talk about what is half-life in mathematics. The half-life is a radioactive isotope. Is the average amount of the time it takes about 1/2 of the items in a sample of radioisotope to decay. Different radioisotopes decay at different rates and can have wildly differing half-life. These half-lives can be as short as a few microseconds and as long as a few billion years. The term is commonly used in nuclear physics to describe how quickly unstable atoms undergo or how long stable atoms survive. Radioactive decay, the term is also used more generally to characterize any type of exponential or non-exponential decay. Okay, here's an example of the half-life. This is a question. Suppose A radioactive material has 10 items initially, so after the first half-life, its number of items will become 5. But what will happen after the second half-life? How can it be 2.5? So based on the knowledge and formula we learned before, we can get the answers. Determining the number of particles NT of the material after a certain period of time, we must take note on that the half-life pertains to the time at which the original amount is halved due to decay. Now we are given the initial number. Initial amount is Ni equal to 10 items. When the first half-life has passed, the remaining mass is half of the original, which is Nt equal to 1/2 times 10 equal to 5 items. Nt such that now when we have an existing Ni equal to 5 items after another half-life has passed, we can solve for the remaining amount. Similarly, so Nt equal to 1/2 Ni equal to 1/2 times 5. So can get 2.5, and it's almost 3 items left.
Wow, cool picture.
And then we'll talk about how the radioactive therapy is used in treating cancer. The radiation therapy, also called radio therapy, right? It's a cancer treatment that uses high doses of radiation to kill cancer cells and shrink tumors. At low doses, radiation is used in X-rays to see inside your body, as with X-rays of your tooth or broken bones. Its purpose is to damage the cancer cells over and over again. The cancer cells don't have enough time to repair themselves between daily treatments, so that they eventually die. Which page? 12. So how the radiation therapy works? The radiation therapy works by destroying cancer cells and damaging a cancer. Oh, can you hear me?
Yeah, sure, absolutely.
Oh, because there is a track outside the house. No. Yeah.
No, we do not hear that, but we hear
Oh,
you.
okay.
Do you want to hear the truck also?
Ah?
Do you want us to hear the truck or no?
No.
No, we want to hear you then.
Okay. And damaging a cancer cell's DNA so that it stops dividing and growing. Radiation therapy can shrink a tumor or completely destroy it. It is most effective on cells that grow and divide quickly. Cancer cells tend to divide more quickly than most normal cells. This makes them more likely to be affected by the radiation than normal cells.
Just hold on a second, Mingxi, on this slide,
okay.
please.
Yeah.
Okay, interesting. It's dividing and growing. Awesome, thanks.
Problems?
No, it's totally fine.
Oh, okay. And how the radiation therapy is used. It may be used alone to treat cancer or with other treatments such as the surgery or chemotherapy. It may be also used before surgery to shrink a tumor or after surgery to destroy any cancer cells that remain and to prevent the cancer from coming back. I have two things to mention. The first one is the external radiation therapy. It's also called external beam radiation therapy. It is the most common type of radiation therapy used to treat cancer. A machine directs a beam of radiation at a cancerous tumor in the body. There are different types of external radiation therapy. And the second thing is the internal radiation therapy. It puts radioactive substances into the body, such as directly into the tumor or into an area of the body to kill the cancer cells. There are different types of internal radiation therapy too. And there are several factors that may affect the treatment, which are the type of cancer, the size of the tumor, the tumor's location in the body, how close the tumor is normal to normal issue. Oh, sorry, this one should be tissue. How close the tumor is to normal tissues that are sensitive to radiation, people's general health and medical history, whether people will have other types of cancer treatment, and age or other medical conditions. So the radiation therapy should only be used when all the factors are at the correct environment. This is a simple summary of the therapy. The treatment for the cancer has two parts, the treatment stage and the recovery stage. The goal is to let the healthy cells and cancer cells coexist. The cancer irradiation periodic solution is globally stable, and the cancer wing periodic solution is globally stable too. It is a primary treatment strategy. This treatment targets rapidly reproducing cells such as those in cancer. So when cancer cells are irradiated, there is a lesser effect or a more slowly reproducing surrounding healthy cells. But it's always a good treatment for in cancer therapy. Okay, thank you.
Awesome, Mingxi. That was brilliant, man. I really enjoyed that. I really enjoyed that. Thanks. It was wonderful.
I thought it's bad.
But no, but man, you caused another headache for yourself. Because why? Mingxi, I have something interesting for you.
Okay.
It was very interesting, and everyone please listen. You can also expand that on your presentation, which you have. I know Aria and Oliver, you are going to have presentations next week. Mingxi, it was very interesting that you mentioned that the radiation therapy is divided in two different parts. The external radiation therapy and the internal radiation therapy, which the internal radiation therapy is essentially the thing that you're looking for. The injections of the radioactive materials like isotopes in the tissues that bears the cancer cells. And those radiations, they just essentially triggers the change in the DNA of the tumors in the body. That was very good that you made the distinctions between the external and the internal treatments. That was more wonderful. And also, you talked about on your second slide. Oh my God, the presentation was fantastic.
The second slide?
Huh?
Okay, let me go back.
Yeah, on your second slide, that's why you cause a kind of a headache for yourself. No, the next one, please.
Oh.
Oh, there you go.
Oh, the
And also,
tracers, right?
yeah, you created a
Okay.
kind of a headache for yourself, Mingxi.
Ah,
You know
okay.
why?
So, yeah.
Because you talked about the tracers, and I just want to specifically assign you a different project. It's going to be much easier, but it's very
Yeah.
helpful for the students in this class. And you
Okay.
talked about the tracers. I want to ask you, please, do a very simple, quick presentation about, let's
The
say, the
tracers.
tracers. Specifically, there is a field, include that one on your field. You're going to expand on it, put that example there. That in the neuroscience, you just talked about the Hodgkin-Huxley model, what is a computational neuroscience? In the neuroscience, and more specifically, in the neurology, which is a medical field to study the brain and cure the diseases. There is a neurological disorder which is called Alzheimer. Have you heard of that?
Uh, Not really.
I'm going to post it on the course website, and you please, I'm just going to add in resources and information. And Alzheimer is a kind of a brain disease that people, when they get it, the brain cells starts to die, and they get a dementia. They become forgetful. For example, they do not. For example, if someone's get the dementia, for example, as an Alzheimer, he or she doesn't even recognize her own son. Everyone becomes a stranger. The memory shrinks, the memory fades, the brain cells dies, and people eventually die. Huh? This is
Mm-hmm.
called Alzheimer's disease. I'm going to post it on there. For the tracers, there is a system. This is called PET scans. I want to ask you, please, you force your all the research on it. This is called PET scans. This is positron emission therapy. I'm going to post it on the course website, all
Okay.
details, no worries.
Okay.
They use the PET scans. It's it's so much fun because we do not want to go to the physics because it's lots of quantum physics. We do not need that because it starts with the electron and the positron, the matter and antimatter. They collide, they release the energy, and it becomes a kind of an MRI system, like the MRI. It is good for the medical diagnosis of the disease, and they use radioactive substances inside the blood, and the
Yeah.
blood goes to the brain. And it's a kind of a substance of the radioactivity of the glucose that the brain feeds on it. Then with the PET scans, they detect which part of the brain has the most damage to that, which it's a kind of a sign for the Alzheimer. You see, then it involves application of the radioactive material with the PET scans to help people, researchers, to detect Alzheimer. Okay, I'm just going to post that on the website. If you do that, I guarantee you're going to get a good mark. It's
Uh,
it, it's a comprehensive research you have to do, but please start working on it. That's a very important thing. Continue to the research which you did. Is it okay,
uh,
Mingxi?
the research is about the tracers.
That's right, tracers for
Oh my
Alzheimer.
God.
Huh?
Um,
I'm just gonna post the information online, and also I have something the same like for Sean. Sean, are you there?
Yeah,
Sean,
yeah, yeah.
and
What
I have
happened?
also the same thing for you. I'm gonna post it on the course website. You please also do a separate research for the proton therapy and ionizing radiation then.
No, no, I have others to do. Is that the yesterday's work?
Sorry, what?
I have yesterday's work to do.
Yesterday's work, what is that?
Uh, I forgot. I forgot the name. Uh, okay, but I will try. Okay,
Yeah,
if I have
thanks.
time, I will try.
Thanks. And the deadline for that, I should say for Mingxi, I should say it's gonna become on next Friday.
well, do another presentation.
Yes, please.
Oh my God.
And for Sean, it's gonna be next Thursday.
Wait a second. For me, what?
You're just gonna talk about continue on the research which you had yesterday to just move on to the proton therapy which you had on your
Please.
slide.
These 2 weeks I have almost 7 presentations.
It's good, man. After that, you have a long weekend coming, and I'm sure you can. Oh, both of you are very smart students. I'm sure you can ace it. And you do that also for the benefits of the class because the others also are going to learn a lot from those ones. It helps them if they want to choose the careers to use the math in those kind of fields then.
Will you mark the Twitter presentation?
Yeah, also it's going to be, it has a mark then.
Only mark me?
No, these ones which you do the extra, these becomes 10% extra on top of the marks which you get. For example, if you're on your final exam, this is for everyone, for Arya, for Oliver, anyone who wants to do extra work like this, you get 10% extra. For example, on a final exam, it's 30%.
Oh,
The final exam is not going to be easy. You get, for example, 20%. You do not have some answers for some questions. Then that 10% complements your 30% then. And it makes sure that you just get above 90 then.
oh, that's good. That's good.
Yes.
Teacher, can you tell us the detail about the extra work on the school object?
That's right. The extra work, I was going to put that on the Schoology then. We had something similar in the past, which was about COVID-19. Nobody did it, but I'm going to post this one, which is related to your projects. For example, Mingxi, if you do the tracers on, for example, neuroscience with the Alzheimer, with the PET scans, which I'm going to put the details on the course website, then you get 10% extra. You get, for example, 20% on your final exam. It raises you to 30%.
Okay.
It's a good deal, huh?
Yeah, that's good.
Yeah. So when we did submit this work?
I'm just going to post it on the website, and it's going to be done anytime before we finish the class then.
Okay.
Yeah.
The next presentation I will do is on next Friday.
Anytime you want before we finish the class. But the tentative is going to be you Friday, Sean Thursday. But it can be anytime before we finish the classes, which becomes by 28th of the month.
Okay.
Yeah, is it good? Is it a good deal, guys?
Yes.
Yes, Mingxi?
Yes. So the next presentation is also 15 minutes or 15 slides.
Yeah, it's gonna be good then. Yeah, even less. Less is even fine.
Oh, okay.
Yeah, it's not gonna be too much. Not too much stress. The purpose is that when we talked about the tracers, also the students know that how can they just expand the math and mathematics into, let's say, diagnosing, for example, the Alzheimer as a kind of a neurodegenerative disease of the brain, that how math can take them forward. And that's a good thing about that then. That's all that we plan to do.
Okay.
It's 10% extra. It's not part of the course, 10% extra. You get, for example, 75% of the final, of the total, you can get to the 85%. Becomes from B, you become A minus then.
Okay.
Is it good?
Okay, good.
Awesome. The same thing for everyone. Okay, guys. Now, the time is, I should say 10.